Okay, let's get started. So welcome everyone to the first session of SYE colloquium series. And today we are very happy to invite Dr. Yu She from Purdue University. So here's a brief introduction to Dr. She. He's an assistant professor at Purdue University, Edwardson School of Industrial Engineering. Prior to that, he was a postdoc researcher in the Computer Science and Artificial Intelligence Laboratory at MIT from 2018 to 2021. He earned his PhD degree in the Department of Mechanical Engineering at the Ohio State University. His research has an intersection of mechanism design, tactile sensing, intelligent control, and robot learning. He is a recipient of Showalter Early Investigator Award and the Google Research Scholar Award and multiple paper recognitions. So without further ado, let's welcome Dr. She, and let's give the stage to him.
Thank you. Thank you. I may just use the mic here, so I just put this one here. Can you hear me from the back? Very good. Great, thanks. Yeah. Thank you, Andy, for the kind introduction, and thank you, Wang, here attending the seminar here. And it's my pleasure to share some research in my lab recently. And yeah, I'm an assistant professor at Purdue University Industrial Engineering. So I want to give a very high-level kind of overview about what we do, maybe just in 1 minute. Then I will talk about what we'll focus for this talk here. So one of the major research directions in my lab, we work on this hardware design. We build a robot from scratch. So for example, if we want to do some particular function, tree climbing robots, so these kind of robots are not available on the market off the shelf. Then we kind of design the CAD files and we build this robot from scratch, and then it can perform the function we want to do. And the second direction is about tactile sensing. I'm going to introduce this very unique tactile sensor. It's quite different from traditional tactile sensor. It can generate very rich feedback from the interactions with the environment. And the last one, when we have the hardware design and we have the feedback, now we can design controller, motion planning, or machine learning policy for grasping for manipulation. So that will be the three major kind of research area. Today, I'm going to mostly focus on the second one and the third one. So tactile sensing and the control manipulation. It may be slightly different from traditional industrial engineering kind of optimization side, but it will be close to the manufacturing or human factor for human-robot collaboration side. So that's the kind of high-level introduction. So you see all these industrial robots, they actually widely used to build cars like Tesla even more than 10 years ago. They're fast. They can do repetitive tasks very efficiently. You saw this everywhere. However, if you take a look about your home, we don't have too much robots there. You saw the robots doing the floor cleaning, and you see the robots for the backyard, the grass mowing, and that's maybe the robots you see in the daily life. It's not like a industrial manufacturing floor everywhere to the assembly things, right? So people work in this direction. We try to have this robot assistant, robot waiter, home robots to help us. For example, I wish I have robots to help us do the laundry, prepare the breakfast, lunch, do the housework. But we are not there yet. People work in this direction. Why we are not there? One major limitation or the critical components we are lack is like this. I'm thinking robotic manipulation, because when we say we have these robots in our daily life, doing laundry, doing the housework, it's a lot of physical interaction between the robotic hand and the environment for grasping, for control. So that's something very different from traditional setting here, industrial robots. In the traditional setting, everything is known. You have a structured environment. And the components, objects, you also know the dimension, the position. But in your daily life, all these things are, we don't know. There's a lot of dynamics and potentially a soft material. In industrial robots, all the components, they're rigid, right? But in your daily life, we have deformable objects, like food, even do the breakfast, right? So all these things create these challenges here. And we think this manipulation is one of the key bottlenecks to apply the robots in your daily life. And within this particular area, robotic manipulation, we think tactile sensing is critical because any manipulation task, it must have the physical interaction between the robotic finger and the objects. So that's where we focus on. My lab focuses on tactile sensing and robotic manipulation. Here is kind of early demonstration from pioneer, Edwardson. This is a demo to show how tactile sensing is important. The participant on the left, everything is normal. She can do this task, lighting a match in a few seconds. On the right side, the same participant, the same task. Now, her hand, her fingers get anesthesia. It's numb. She has no feeling on the fingers on the tactile. Eventually, she still made it, but it takes much longer, more than 30 seconds to do the same task. So we just want to see tactile really important in your daily manipulation task here. For example, you tie your shoelace, buttoning your shirt, folding your clothes, do the zip lock, doing the breakfast, do this all like assembly task. All these things we need a tactile. And of course, people working in this field for a long time, these kind of traditional tactile sensors, they have a significant progress in the past, say, 20 years. Piezo-based tactile sensor, capacity-based tactile sensor, resistive-based tactile sensor, they're great. They provide big, they have big in progress in the past decades. They have some limitations as well. They kind of complex design for the fabrication process. They have limited spatial resolution. And you can imagine if you want to have, say, 10 by 10 matrix, how many cables you need, right? You have a cumbersome wiring problem. So this is one kind of tactile sensor. That's not the category of tactile sensor. It's called a vision-based tactile sensor. They are quite different from traditional tactile sensors. The idea is like you have an embedded camera within this sensor. Actually, from the next slide, I'm going to tell how it works. It's quite different from traditional tactile sensors. So first, we get a clear elastomer, silicons, and then we coat a reflective ink on the surface. So it's just coating. And then if you press objects on the surface, it's going to deform the gel here. And if you assemble the gel and the coating to the robotic fingers, if you just assemble these components to the fingers here, then it becomes a tactile sensor. This is the gel I just mentioned, and this is the coating, and we now add the LEDs within the robotic finger, and we add a camera within this robotic finger, and then it becomes a vision-based tactile sensor. So these are the traditional, the recent kind of progress in this field. So that is how it works for this vision-based tactile sensor. Now, because we have embedded the camera within these sensors, we can tell the raw data from the image. So you can imagine this difference, how rich information we can get from this vision-based tactile sensor. Traditional tactile sensor, you have resistant, capacity-based. This sensor maybe give you one dimension or a few dimensions of the data. Now, we basically convert a tactile to a vision problem. And for images, you can easily get 1 million pixels, 1 million dimension. So we get much high resolution data, much high dimension tactile feedback. Then we can think about how can we use, for example, computer vision, machine learning algorithm to process this data, to make sense of this data, and use data for robotic manipulation. Whatever things that we need, we can just use some computer vision, machine learning algorithm to process these images, to get the data what we need. So among all these tactile sensors, we are working on this one. It's called the CSAIL. So it's also vision-based tactile sensor. It's a pioneer in the field. I mean, the early stage, we kind of still in the pioneer area. And there's a reason behind this, why this vision-based tactile sensor get very popular in the past 12 years. Because 2012, right, deep learning they get a huge progress since then. And now I just mentioned this, tactile sensor convert the tactile feedback to the computer vision. And now you can immediately use this machine vision, a deep learning algorithm to process the tactile data. And that's the reason it gets very popular in the past few years, 10 years. So now I introduced how this tactile sensor works. And here I just want to give you a visualization in a second, how it looks like. So the early version, this CSAIL is made by Jonathan in my postdoc group. So early stage is like 1 inch by 1 inch by 1 inch cube. Pretty big, not appropriate for robotic manipulation. Later on, my colleague, Siyuan Dong, made a smaller version, excuse me. So this version, the first time, they tried to install this sensor on the end effector on the robotic arm for grasping for manipulation. Still, they're kind of bulky here. They cannot access to small space. And then later on, I joined the team, made a smaller version to make it smaller, like a finger size, and make it edge the shape so it can access to confined space. It's more appropriate for grasping or for manipulation for robotic system. Now I just want to give you a kind of visualization, what kind of tactile data we can get. And later on, I'm going to show you how can we use this kind of tactile data for grasping, for manipulation. First, this is the same sensor I mentioned earlier, vision-based tactile sensor. We get an embedded camera within this robotic finger. You have soft gel here, LEDs inside, coating on the surface. Now, if you have a finger, press the surface, it's going to deform, right? So here, this is a camera view. The camera was embedded within this finger. You can see the geometry first, like the fingerprints here. The yellow arrows representing the shear force or tangential force. This is a demo. We press the nut on the sensor, and this kind of tactile data we can get. We get a lot of information, very rich information. We can extract some of them. For example, on the right side here, this is the depth information. That means the normal deformation we get from this sensor. We can use some computer vision algorithm to get this depth information. If we apply the inverse finite element method, we can convert this depth information to the normal force distribution. So that's different from traditional tactile sensor. You can imagine the capacity-based tactile sensor, resistive-based tactile sensor give you one dimension resultant force on the normal direction. Now, we can provide you the normal force distribution. It's not a resultant force. You have a distribution, could be very high dimension, depends on what you need, right? Second, we can get these yellow arrows, which is shear force, friction force. Most of tactile sensor cannot provide this information, but we can use this Mach tracking to get this shear direction, the force in the shear direction, and not only the shear force, but the distribution, because we can get these markers array on the surface of the sensor, so we can get whatever dimension you need. So that's the two information. Second, the third one, we get the sliding information. For example, we are grasping some objects. It's going to slide, but not slide yet. We can detect, hey, there is a slide going to happen, and we should increase the gripping force accordingly to prevent the sliding. So that's the rich information we can get. And also we can get the orientation as well. So for robotic grasping, assembly, manipulation, the orientation is very important. You can imagine if you insert your key to the keyhole, two things very important. First, position alignment. Second, orientation alignment. The key must be perpendicular to the keyhole to do the insertion. You can imagine every single pegging hole insertion needed this information. Insert the key to the keyhole, USB connection, your AirPort insertion, the outlet insertion. Every single insertion, you need this position and orientation alignment. So we can get this information as well. On the left, we show this live demo, human rotate a cube on the sensor. On the right side, we get this tiny bit tactile feedback. In the middle, we can reconstruct the orientation and the position of the objects on the fingers. So that's some visualization, what we can get here. We can get much more. Here, I actually have maybe bring a question you can think about a little bit. This tactile sensor gives you very high dimension data, for example, 1 million pixel. But if you want to control for manipulation, the most traditional controller, you have 1 dimension, or very low dimension for control. How can you bridge the gap? You have 1 million pixel input from the feedback, but in your output control, you only have 1 dimension, low dimension. How can you do that? So later I'm going to show you 3 methods. How can we make sense of this data for grasping and manipulation? Now I just bring the question here. Next step, we introduce additional tactile feedback. So like a human do any manipulation, assembly task, not purely based on tactile. Human have different sensor modality. Vision, 60 to 70%. You have tactile, you have acoustic, you have multimodal sensor, right? We try to add additional sensor modality here. So on the right side, the same sensor I showed you earlier. Vision-based tactile sensor, purely tactile. On the left side, it's vision. So this is the same finger, the same sensor, but it has 2 modalities. We just can do some simply electrical signal control. We can have the tactile or the vision for 1 finger, for 1 sensor. So this is the because we already have camera embedded in the finger, right? If we make this surface, the coating material, transparent, so it can see through from the finger and see the objects on the table. This is the see-through image. It can see this pair, so just a regular camera, computer vision, right? And if we make this opaque, it becomes a tactile sensor. So how can we achieve this dual function modality within 1 finger, 1 device? So we used something simple, one-way window glass principle, and the bright side acts as a mirror, and dark side acts as a normal transparent window. You can imagine, so like in the daytime, the outside is lighter. The inside of the sensor or inside of the room is darker. If you stand outside, you see the window. It's just like a mirror, reflection. But if you stand inside of the house, inside of the sensor, you see the windows here, it will see through. If we turn to the evening, that's upside, right? Vice versa. So that's basically how it works. Basically, you can change the lighting condition to change the mode, either tactile or vision. That's how we achieved this functionality. I'll show a very quick demos here. So in here, we turn off the light. So the outside lighting is stronger than inside. It's a vision modality. As you just saw, it's a vision modality. Now, we change the lighting condition. Here, you see, we turn the lights on. Now it becomes a tactile modality. So we just need to simply change the lighting condition to get either tactile or vision. Later on, we have some demos to show some tasks. We use both tactile and vision to finish some tasks. I think this is a pegging hole demonstration. We first using vision to identify the position and orientation of the objects on the table. Excuse me. And then we grasp the objects. Here's vision modality to identify the object's position orientation, do the grasping. Once we grasp the objects in the hand, we switch to tactile modality, because tactile modality can tell you very precise orientation of the objects in the finger, and then you can do the packing hole insertion using this tactile feedback. That's one of the demo we showed early. Simple demo combine both tactile and vision. But we also want to add additional tactile modality, which is the acoustic feedback. For some of the tasks, like here we show buckling. So when you do the insertion, at the end of the insertion, you will hear a click sound. So we can use this acoustic feedback to tell us the state of the insertion task. So once we hear the click sound, we know the task, the mission is completed, right? So we combine this tactile and acoustic in a single sensor. So this is the latest sensor we made. On the left side is still the traditional or the tactile sensor I showed you early. Vision-based tactile, you press a key, you see the tactile imprints. On the right side, we show the new added acoustic feedback. Basically, we just add some, for example, accelerometer, microphone on the finger, and you get this accelerometer information, and you can do a faster Fourier transformation, you get a spectral information. And if you tap here, you saw all this acoustic feedback. And next, we're going to show some, this is the pipeline. Later, I'm going to show the demos. We combine these two modalities to perform some manipulation task. So here, the first step, we have this robotic arm grasp this pen in the robotic finger. And this vision-based tactile information tell us the position and orientation of the pen in hand. Then we can do the alignment, do the insertion. At the end of the insertion, we will hear a click sound by our acoustic feedback, and it will tell us, hey, mission completed. So we combine these two information for assembly task. This is a simple demo. First, we're using vision-based tactile information to do the alignment, position alignment, and orientation alignment. And the tactile here, vision-based tactile here, and now you do the insertion. At the end of the insertion, we will hear a click sound, and it will tell us mission completed. Tactile, vision-based tactile, and then insertion. Until now, everything I discussed is more about tactile feedback. Now I'm going to introduce how do we make sense of this data for grasping and manipulation. The same question I raised earlier. You have very high dimension tactile data, 1 million pixel or 500,000 pixel data. Dimension is like a very rich information. On the other side, for control, for robotic manipulation, you only have either one dimension or very low dimension. How can you bridge the gap? I'm going to introduce here, but you may think about a little bit, how can we do that? I'm going to present 3 ways to do that. First, we can extract the low dimension data from the high dimension data. For example, we downsize the dimension. The original dimension for this image data, say 1 million, 500,000. However, for control, for manipulation, we don't need that high dimension. We just extract whatever we need. For example, for this cable manipulation task, we downsize the dimension from 500,000 to 3 dimensions. For this example, we want to do this cable manipulation. The robotic arm grab this cable, follow the cable, find the end, and insert to the plug, to the hole. For this task, you don't need this 500,000 pixel dimension. We just need 3 dimensions for traditional control. For example, the position, orientation of the objects within the robotic finger. The contact area or the contact force, that's something we need. We extract this high dimension data to low dimension tactile feedback, and we can insert to the controller for grasping for manipulation. So that's one of the first way we can do that. So this is kind of how we downgrade or downsize the dimension of the tactile data, make sense of the tactile data. The white ellipsoid showing the contact area, which is important, is corresponding to how much force you grasp on the cable. The red ellipsoid, the red line here, I just stop this one. I'm going to spend maybe 1 minute here to explain how we use this data. The white ellipsoid showing the contact area is kind of proportional to how much force the robotic gripper grasps on the cable. And we do a principal component analysis, PCA, we can find the principal direction, which is the orientation of the cable in the gripper. This is also important. And also we have the shear force, the friction force, which is represented by these yellow arrows. Then we can use these three data for control. We have some traditional low-level, low-dimension control, PID controls, LQR control, MPC, model predictive control. All of them are low dimension. And here's the automatic demonstration using this tactile data for insertion. Again, this is the This is a demonstration for this task. Using purely tactile data, we need to design two controllers you can imagine. First, if we don't apply any controller, this cable is easily falling out from the finger. You need multiple two controllers. First, we need to move this gripper back and forth to prevent the cable from falling out. So one controller. Second controller, we want to make sure the gripping force just right. You cannot be too large, cannot be too small. If the gripping force is too large, there's too much friction. You cannot slide smoothly. If too less gripping force, then we don't have tactile feedback for control. So that's two controllers to regulate this robotic arm to move back and forth and the gripping force to make sure this cable manipulation fully smoothly do the task. Again, this task is just following the cable, find the end, insert to the cell phone using purely tactile data. That's one way. How can we use this tactile data? That I just mentioned the one way. We extract explicitly from the 500,000 dimension to 3 dimension for traditional control manipulation. Now I'm going to introduce another way. This is a second method that we can do to how do we make sense of this tactile data. So like the task we did early, here we can also use the same procedure as we did early for grasping for manipulation. However, if we want to apply this grasping policy in our daily life, you can imagine that will be very difficult because, hey, I have different stiffness of the objects, different shape, different stiffness, different mechanical property. I can design PID control for the banana, but it not necessarily works for the egg. And I can design another PID control for the egg. It not necessarily works the onion rings. You have different objects. I design different PID control. It is okay, but many times you have a lot of objects you've never seen before. You can simply impossible design infinite PID parameters for every single object, right? So that's how we find another solution. We combine machine learning and model-based control to address this problem. This is what we do here. Again, this image input from Tactile, you have 500,000, 1 million pixel. We use the machine learning, just as in an MLP. We kind of extract the data to an implicit low-dimension representation. So it's low-dimension embedding, 40 dimension or 20 dimension, I forgot the number. But this low dimension is kind of an implicit representation, including all the physical property, the friction force, normal force, this geometry information, the force information, is a low embedding. We don't have an explicit representation, but it's just embedded in this low dimension data. And then we formulate the grasping problem as a MPC, model predictive control. So we can kind of train a policy. It can grasp whatever objects in a robust manner without destroying the objects. Here is how we train this policy. We collect some samples for training the sample, very soft objects, just silicon. A little bit rigid, the phones. A little bit rigid, is another silicon rubber and a 3D printed material. And we have a series of kind of data collection, and then we train the policy. Later on, we can grasp whatever objects we never seen before, very robust, without destroying it. You see some objects here on the ring, quite fragile. Some objects X is also fragile. And some objects are a little bit more rigid, but our controller can be adapted to whatever objects we never seen before. And later on, we are going to show some more interesting result. So here we just show the grasping experiment. All these different objects, not in your training set, but we can adapt to these different objects. Second, we show even if you have some dynamic motion, like inertia, you spin some objects in the finger, you see our controller can adjust the gripping force accordingly to prevent the objects from falling out. And if you have unexpected collision, our controller can also adapt the gripping force to maintain a robust grasping without destroy the objects. So that's tactile control. So now I mentioned the second method. How can we make sense of this tactile data to grasping controller? This is still the second one. The third one I'm going to introduce a little bit later. This one is more about in-hand manipulation. So all the grasping I presented earlier is just 1 degree of freedom robotic gripper. That's all. What do we do? Just pinch force. 1 degree of freedom, 2 fingers. Now we add a little bit more degree of freedom or flexibility here. We now have 5 degree of freedom. The robotic finger can do the extension here, gripping here, and the rotation here. So you have 5 degree of freedom. My lab also have this kind of dexterous hand, just like a human hand. It's a little bit more complex for grasping for manipulation. I'm not presenting today, but here it's kind of show the idea, high degree of freedom robotic gripper. You can do some in-hand manipulation that can not be done within these 2 fingers or 1 degree of freedom gripper. Of course, my lab focused on this tactile sensor. We will install this tactile sensor at the fingertip. And later on, we're going to show you this high degree of freedom gripper can do some in-hand manipulation using this design here. Here's the task we did. We have some objects buried within the granular material. And this red object is something we are interested. But in the beginning, when we command this gripper grasp the objects here, in the beginning, you saw all the tactile feedback is a granular material. There's no tactile feedback about the target objects. So we need to do some in-hand manipulation to get rid of this granular material. Then we can get some good tactile feedback, good quality of the tactile feedback of the target objects, right? So that's what we did here. So we kind of squeeze a little bit to get rid of the rise. Yeah, we squeeze a little bit, get rid of the rise. Now we have tactile feedback for the target objects. Then we can do the classification based on the tactile feedback. We showed a little bit different objects, manipulation, grasping, in-hand manipulation. And here is some data we get from 9 or 10 different objects. We can also do this scoop manipulation because, for example, we want to insert this credit card to the credit card holder. We need to first grab this very thin credit card on the table, and then we can use this tactile feedback if you see, once we grasp this tactile feedback, we can do some in-hand manipulation here. You see there's a rotation in the finger, and then we can align based on the tactile feedback to insert the credit card in the credit card holder using tactile feedback. So this one kind of combine the in-hand manipulation with the 5-degree freedom and the tactile feedback for the alignment for the insertion. We can also use this data for cable disentangling using the same framework I just presented earlier, the tactile feedback and the in-hand manipulation. So the only difference compared this one and the early one is we add this additional degree freedom for this robotic gripper, so it has more flexibility to do in-hand manipulation to do this kind of manipulation task. Until now, everything we discussed is about static or quasi-static manipulation. Now we're going to introduce another one, dynamic manipulation. And here is the third method I mentioned. The first method, we downgrade the 500,000 tactile sensor data to 3 dimensions. We can design controller LQR, MPC, PID for control. Second method, we combine machine learning and model-based control because we know how to formulate the grasping problem as a mathematical formulation. We can combine this together. Now, for a little bit more complex task, dynamic manipulation, we actually don't know how to formulate it as a mathematical representation. So we just use machine learning here for dynamic manipulation. And in this way, we can use the raw image data, raw tactile data, very high dimension, a lot of computing, but at least it can do the task, right? That's 3 ways we make sense of this data. Again, I just go back one more time here. I first introduce the pipeline here. It's a recycling machine, fully autonomous. Grasp this, dart. The task is we want to do the dart throwing. The robot grasps the dart and hit to the target, and we have a 4-bar mechanism here to automatically detach the dart and automatically flow back to here, and then automatically go here. And I can grasp again, throw again, and grasp again, throw again. Everything is automatic. Then we can, using the reinforcement learning pipeline, to train a policy to do the task. The new things here is we introduce tactile feedback in this pipeline, and we're going to show you this pipeline can be applied to something we never seen before, not in your training data. So this is the data collection. The observation for this pipeline, we grasp this dart. We actually were going to shake a little bit, tilt a little bit, and we saw all this tactile information during this shaking or tilting. Actually, this information is very important because it encodes the mechanical property from our tactile sensor. For example, the mass distribution. All this data can be captured by this raw image data. So later on, we use this data, and of course, we have this action. Action here is 2 actions. One action is like, what's the depth position we're grasping the dart, HO, is one of the action parameter. Another one is orientation of the dart within the gripper here. We have the observation, we have the action, then we can train a reinforcement learning policy to do this task. One thing I want to mention is like this. Because we have this new tactile sensor that can capture the physical property of the objects. That means later on, I give a new dot, never seen before. I grasp this dot, I can estimate the physical property. Then I can generate, I can generate the action accordingly to throw the dot. Even this dot I've never seen before, it could be heavy, longer, different property we can capture from our tactile sensor, and then we can generate the action accordingly. So this is some of the tasks we showed. So we have 3 dots we saw before, but we have also 2 or 3 new dots we never seen before, and we showed we get a very accurate result. we also did a little bit surgical application or healthcare application for tactile exploration, because we think about some medical application if people have unhealthy tissue, for example, tumor underneath of the skin that cannot be captured by images, cameras, human eyes, but we can tell from touch, from palpation. So we want to use this tactile sensor to estimate the physical property of the tumor. So we showcase this physical 3D representation of the objects within or underneath of the skin. We tried different objects. For example, this is a hemisphere shape, this is a crescent shape, and we can do this tactile exploration to find out the tumor information. Excuse me. There's a short video here. So there's two things we introduce here. First, impedance control. We must adjust appropriate contact force on the skin. Second, we have some motion planning algorithm to make it more efficient to only explore the interested area. And there's three information we can get from here. First, whether or if there's a tumor underneath of the skin, we can do that. Second, if we have that information, can we localize, reconstruct the shape of the objects? And we did it here. We can do the 3D reconstruction. We can reconstruct the shape and the size of the objects underneath of the skin that cannot be seen by cameras or human vision. And the third task we didn't show here is some latest result. We can also estimate the physical property of the tumor underneath of the skin. We can estimate the stiffness, hardness, and viscosity of the tumor underneath of the skin. And we assume this mechanical property may correspond to the stage of the tumor, early stage, middle stage, late stage. Maybe the stiffness, viscosity will be different, right? At least now we know the stiffness, we know the hardness. It could be formulate a mapping to the stage of the tumor. We also have different applications in addition to the task I showed earlier. Oh, that's one task I forgot to mention. We have some latest result. I didn't present it here, but I think it may be important here. I want to mention. So this is a 3D reconstruction of the tumor or the tactile information. We actually have some recent work can physically reconstruct the physical shape. For example, you can imagine we have some robots on the Mars do some teleoperation. And we actually not only can get this tactile information for the tactile sensor, we can also reconstruct the geometry that we can feel, human can feel. You know, this is one, this is two. I can tell the geometry, reconstruct the physical information for this tactile information. If anyone interested in that direction, I'm happy to chat later on. And of course, we can do different applications for industrial assembly, gear assembly, belt assembly, cable assembly. This is the NIST assembly board. We have this in the lab. We have a lot of agriculture application using this tactile sensor and motion planning algorithm I showed earlier. And we can do dual arm manipulation coordination. We have some early work on deformable objects manipulation, which is the cable and also fabric manipulation folding. We have some in-hand manipulation. Also have power grasping for manipulation. Those slides I present until now is more about the tactile and manipulation. I also very briefly mentioned some of the hardware design work. This is the build from scratch. We build a 3D design with 3D printing, laser card, we assemble with testing. So these are some hardware mechanical system we also made before. I didn't present it too much today. But that's basically all the slides I prepared. I'm happy to take any questions you may have. Yeah. Thank you.
So I have a question. Probably I first ask. So in your raw, what is the format of your raw data from these tactile sensor? I saw that there are some alignments like these arrows, right? And also you also mentioned, I also see that there are some colors reflecting some other information. What are they?
So I get the second part. Can you say the first part? I have the microphone here. I get the second part of the question, but what was the first part? Can you remind me?
So I see from the raw data, you have these multiple arrows to denote the alignment or this relative location. And another thing is that we have these different colors, right? So what are these data? And it seems that their, how to say, resolutions are different, right?
Yes, exactly. The yellow arrows representing the shear force or the tangential force. The resolution, of course, is different from the image data, the RGB data. These arrows is kind of generated by the mark tracking. And these markers, we can customize the dimension. Here, I think we presented like a 10 by 14 arrow array, but depends on what you need. For our application, this is good enough for grasping for manipulation. If we need a high density, we can also do that. So basically, this is just optical flow. We can track the marking. And for this RGB data, there's a reason why we use this RGB data, because we want to use some computer vision algorithm. It's called a photometric stereo. It can convert this RGB intensity to the depth. So that dimension is pretty high. It depends on the camera. We can also customize by ourselves. For example, if we need 480 by 640, or we just need like 120 by 240. It depends on our need. We can customize the dimension as well. Basically this RGB data is used for 3D reconstruction and to get the depth information. And this mark tracking is to get this shear force. So it's kind of orthogonal. The RGB data get the normal force estimation. The mark tracking get the shear force. They are orthogonal, and they are both very important for grasping for manipulation. Is this answer your question?
Yeah, sure. Yeah,
okay,
thank you very much. And these results are really, really impressive. I know that you focus more on these outcomes instead of methodologies. Yeah, so other questions?
So first of all, thank you for your presentation. It's pretty interesting. So I have actually two questions on your topic. So first one is you talk about use the gel-like sensors. We have a higher dimension results, right? So I'm thinking of is the materials is to the specific gels, or you can use other like biomedical materials, because it can, from my perspective, like I think it probably are good, good materials or good ways to be an artificial skin, to for the skin recovering or something. So is that the specific material you have to use can achieve these sensors? This is the first question.
Yeah, great. Yeah, thank you. A short answer is no. We don't need a specific material as long as it's transparent. So because we have camera see through the gel and see the reflections on the coating, right? As long as it's reflective, it's good. So we don't need a very specific material. However, we do try using another material. I have a recent collaboration. So for that material, we no longer need RGB illumination, because the material itself will react to the force. For example, different force, the material will generate a different color. So that means we no longer need the RGB color to provide the illumination. Now, the material itself will generate a different color, depends on the force applied. So that could be another option, and we have done that before. That could be a good direction. So yeah, short answer, we're not necessarily restricted to the material. It could be different material, could be some bio-based material. Yeah, you have a second question?
Yeah, thank you for your answer. And the second question is like you designed different tasks for your robot arm, and you talk about the different method you do different types of the work. So I'm wondering if for the complex the work, if there is a more general way, or how do you deal with this, task using a more combined methods or, general methods to do the control? Is there any?
Yes. So that's exactly the way we are using three different methods. So the traditional model-based control, I showed you in the first task, cable manipulation. It works for the cable manipulation, and even we show it actually can be generalized to different cables with different dimension, material property. We have varieties of the cables. However, if you say you want the same framework for fabric manipulation, make a break first, that's a different story. You may need to redesign the controller. So that's the reason we mentioned to the second one. The second one, actually, we're using this hybrid physical informed machine learning. So you combine the machine learning for this latent space implicit tactile representation embedding and the model-based control. So in this way, the second task I show grasping different objects, it can be applied to all kinds of new objects we've never seen before. So that's some kind of generalization applied here if we get this machine learning in the pipeline. The third task, data throwing, actually is more generalized. For some tasks, we even don't know how to formulate the mathematical representation. Then we're just using this machine learning. My lab also working on this reinforcement learning and also imitation learning for different manipulation tasks. That could be more, for some tasks we've never seen before. So I agree. If we can first formulate the mathematical presentation, that would be the best situation. For some tasks, if we cannot, maybe combine, physical informed machine learning could be potentially more generalized to different objects manipulation. Yeah.
Thank you.
Thank you.
Yeah. Other questions?
Thank you for this interesting talk. So I just have a general question about the tactical sensors in robotics. So this concept is not new, right? The tactical sensor has been used in robotics for many applications. So can you clarify a little bit more clear about this contribution? You more focus on like designing better tactile sensor, or you focus on more like tactile sensors in different robotics applications? So because you didn't show some literature review, so I want to gauge better about what is the contribution your group mainly focus? Yeah.
Yes, thanks. There's two questions. There's two things here. One thing is about the tactile sensor. The second one is robotic manipulation. For the tactile part, the CSAIL family is kind of the pioneer in the field. At least 3 years ago. For now, I don't know. So our contribution is you see the original tactile, the CSAIL-based tactile sensor is 1 inch by 1 inch by 1 inch dimension. It's not possible for robotic manipulation. We kind of using this concept for grasping manipulation. So the original principle, how do you say, the tactile feedback we get, for example, the depth information, photometric steel, originally is in the computer vision community. Nobody used it for robotics, grasping manipulation, and tactile. Now, we convert a touch information to computer vision problem. So that's the earliest work from the CSAIL work. Convert the tactile, traditional piezo, capacity-based tactile sensor to a computer vision problem. Now, all the machine learning tools, computer vision tools, you can leverage it for robotic grasping manipulation with tactile. So that's something new here. Second, we add all different modality here. As you see, like human, tactile itself is difficult to do some complex manipulation. We need to combine, vision modality, tactile modality, acoustic modality, and you need to integrate together for some complex manipulation. And also that's something new in my lab. So that's one direction. The second direction is about manipulation side. So our lab is developing this kind of combine this model-based control. We formulate the grasping problem as a mathematical representation, and we combine this machine learning with the tactile information, and then we combine these two together, and then we can do complex manipulation, and it can be generalized to different tasks. So that's something new in the manipulation side. So the two directions, one is tactile, one is manipulation. Yeah.
Very, very interesting. So I have a question about this tumor sensing. So I could imagine that could be very, unpleasant for the patient if you're kind of poking around the skin. So what is the force that you're, using to do this sensing?
Yeah, so actually they have some like ISO, International Standard Organization, about what's the maximum force you can apply to the human skin. I think real speaking is like a 50 Newton. They also have the pressure threshold. We just follow that threshold for this tactile propulsion because we are doing this impedance control, or you can think about it like a force control. We can maximize the force applied on the patient. It can be customized by everyone. If we want to apply 3 Newton, that would be 3 Newton maximum. We can follow the contour. If the shape is like this, we can always maintain the interaction force is 3 Newton, no matter what the shape you interact with.
If your force is lower, you're not going to get as deep into the tissue in terms of sensing, right?
Yes. So that's very cool, a very good question. So for here, we follow this ISO standard, and we also try different depths of the objects underneath of the skin, right? We tried that experiment, and we show actually under the skin 2 millimeter to 8 millimeter within 5 Newton, we can get a good result. If you get a very deep, no, we cannot get a good information. We have some threshold. Yeah.
Thank you.
Yeah. Thanks for your talk. It's very excellent work.
Thank you.
So I have 2 questions. The first one is about the video, the very impressive video that the robot arm get a strawberry buried in the sand. So I wonder how precise the touch sensor, like if two things like buried in the sand, they are with similar size and shape with just a little difference. Can the touch sensor tell the difference between the 2 things and touch and take out the thing that the engineer want?
That's a very good question. We have a terminology for the question you mentioned. It's called singulation. Mm-hmm. So you can imagine if you have a box of a screw, like a human do, you just close your eyes, you grab, put your hand in that box. Yeah. Actually, you will grab a bunch of these different screws, not only one, maybe 10. Actually, you will do a little bit kind of squeezing again, and remove all other screw, only left one in the finger. It's called a singulation, that terminology. The same principle here can be applied to the one you just mentioned. Here, the target object, the strawberry, is much larger than the granular material. So it's also singulation. You do a little bit squeezing, get rid of the granular material, only left one in the finger, right? Same idea can be applied for the singulation for the one you just mentioned. If I have different objects with the same size, all screws have the same size, we can also do this singulation to get rid of the material and only left one in the finger. And if we have different objects within the finger, we can immediately tell because we can get the geometry information. The geometry information can immediately tell us there's 1 object or 2 objects. If it's more than 1, we will continue to do this singulation until left only 1 in the finger. Yeah, that's a very good question. Yeah.
Okay, yes, thank you. And I have another small question. So I know that the tactile mode can measure the shape. So can the whole system measure the size of the thing that it take?
The dimension of the objects? Of course, we can do that. I'm not sure if I carry the question, but if we were talking about this, kind of the overall shape of the overall size of the objects, yes, but the object could be larger than the sensor, right? We need to do a tactile kind of, steaming together. You kind of combine different tactile together. People working on that direction, but my lab didn't work on that because, yes, someone already worked on that. Is this the question you're asking?
Yeah.
Yeah, you can just stitch all these tactile together, assuming there's no lighting. For example, underwater, there's a lot of occlusions and you can't see clear, and you need a tactile to find out the size of the objects. You can do this, propulsion multiple times, and then you can stitch all these images together. You can formulate the dimension, the shape of the objects. Yes.
Thank you.
Thank you.
Okay, so let's thank our speaker again for the great talk.
Yeah. Thank you. Thank you.
Yeah, and this is the end of this colloquium. Thank you.